Ellen. Ellen is the head of product at Tilt, which is an amazing tool for developing on Kubernetes. And this talk is about control loops and application development framework. Would you like to share your screen, Ellen?
Yes. So I'm gonna leave the window not full screened like this because it's weird if I full screen. So you're gonna have to endure the little menus here from this thing. All right, so it's good that Natalie's talk was before because it laid some groundwork to what I'm gonna be talking about here. And just a little funny thing, I'm preparing this talk together with a coworker and he added a bunch of pictures like this one. And I have not reviewed this, so we might be surprised. So let's see what happens. So in this talk, we're going to talk about control loops, what they are, what they do, what they're for, how this is related to Kubernetes in some way or not. We're going to talk about some ways that we used those control loops and lessons we learned with that and whether you should care about this or not. So control loops are kind of what Natalie was talking about when it comes to operators. So a control loop, it's something that like I'm watching the environment. When something happens, I need to do something. That's a control loop. So the thermostat, the room is at a certain temperature, the temperature lowers and then the thermostat kicks in and the heater turns on. It brings the temperature up. Once the room is at X temperature, then it shuts off and waits for the temperature to go down again. That's a control loop. ABS brakes, the same thing with, it doesn't want the brake discs to lock. So whenever it senses that it's locked, it releases and then it presses again and it does that very quickly. My colleague added drinky birds, which apparently it's this. If you know what that is, I hope the example helps. And we all wish we had a control loop to water the plants. I can see Natalie has this under control. Natalie's plants look healthy. I certainly wish we could automate this because my plants are very sad. Anyway, when it comes to software, we have Zoom running here, and if my internet were terrible, I would be more pixelated, but things would still keep going. Because my internet's great, then I'm less pixelated than otherwise, and it just adapts that way so that the call can continue despite changes in the internet quality. Other control loops people might be familiar with, NodeMon. It's that JavaScript thing that when you change a file, it rebuilds your thing. So once again, it's watching, something changes, it takes an action. Your linter, so you write bad code, like you write some code, the IDE runs your linter, you did something bad, it puts a red line under your bad code, etc. Those are control loops. Kubernetes is a major user of control loops. Everything in Kubernetes is a control loop. Everything in Kubernetes revolves around the control loop. Especially because of the declarative state management thing. And this book, which I think I have in here, this book is a great way to read more about declarative state management if you're not really familiar with it. So it basically means that with Kubernetes, you don't say do this, then do that, then do the other thing. With Kubernetes, you say, I want this to be the ideal scenario. And Kubernetes is going to do whatever it needs so that that becomes the ideal scenario. And if something changes at runtime, it's going to detect those changes and react to them so that the declared state is reached. So why is this relevant? Unix has this concept of everything is a file. So, oh, you want to read from your webcam? That's a file. Oh, you want to make coffee? That's a file. Oh, your dog is sick? That's a file. With distributed systems, instead of everything being a file, everything is a server. So, oh, you want to know how many users we have? There's a microservice for that. Oh, you want to talk to the database? Microservice. Oh, you want to see the web page? Microservice. Oh, something you need to see if the security is something microservice. I don't care what it is, it's a microservice. Now, those services, they have their configuration, which you use to spin them up, but they also have runtime inputs. So to use the Kubernetes example, you're running your system, which it was deployed as you configured it, but then a pod died. So now we need to spin up a pod again. Or maybe we're trying to spin up this pod, but there's some restriction that says this pod can't run on this node. So find me another node to put this pod in, etc. Control loops are basically the tool to react to runtime conditions. And Kubernetes has both been a driver of this trend of using control loops for everything, and has also been reacting to this trend because it was already there before. Now, anything that works with or similarly to Kubernetes needs to be a control loop too, and that's why everyone's doing operators, because if you're doing stuff that's going to play ball with Kubernetes and it's going to run with Kubernetes as Kubernetes runs, it needs to be in the control loop format as well. It needs to be in a similar control loop as Kubernetes. So let's just use the exact same control loop and make it an operator. So that's why operators are so popular, because it's basically the application development framework to make things that interact with Kubernetes. So let's look at some more details about Kubernetes. Kubernetes is pretty simple, despite what people say. Interacting with Kubernetes is not hard. You have a CRUD, so you can create, read, update, and delete resources on Kubernetes. The distributed systems, you can click this learn more link here below to read more about how this, the why of things. But you basically take a traditional CRUD, you add list and watch, and suddenly, basically, these are all the verbs you need to interact with a control loop. With those, you can have a controller, which is, the whole thing Natalie talked about. It's a thing that's running there, and it makes sure your stuff works. I had not seen this image. This is very confusing. Everything is a mirror of the Go struct. Yes. I don't know what Nick, my colleague, meant with this. Okay, let's move on. What in the hell is going on? Implementers use a native API. Users get a simpler. Oh, yeah. Okay. So one thing that's cool about Kubernetes is that the people writing Kubernetes and the people using Kubernetes use the same API. That's not the case for many applications. A lot of the time, you have two APIs, one for people who work at the company and the other for users to use. You can never make the two APIs good. It's always one is the good one, the other is the bad one. Usually users end up with the bad one. You can see a picture of the bad API here on the screen. So the good thing about Kubernetes is it's the same API. So you can always see the status of everything in the cluster, of all the resources and what everything is doing. You can always do those kinds of interactions using the same API. So I'm writing an operator, you're deploying a pod, my friend is making changes to API machinery, to Kubernetes itself. We're all using the same API. That's important. We're going to get to that in a second. And what in the hell is this? Okay, Maslow pyramid of needs. Apparently self-actualization means controller runtime. Esteem means CLI run. Okay, I don't understand this. The point is that controller runtime is a part of Kubernetes that monitors. Okay, now should we start from the bottom? Right. Okay. So Go structs are basically how you define things. Like, oh, I want my pods to have 3 replicas. You insert that data as a Go struct, and that can be then interpreted via Gamma or JSON or whatever you want. API machinery. I might be getting this all wrong because this picture is confusing, but I think API machinery is the thing that gives you the verbs. So you can create a resource, change a resource, update, list, watch, etc. API server is going to, I think API server does the actual control loop of things. So when something changes, it tells the thing that was watching that the thing changed, and then it receives other requests, etc. CLI runtime is the command. So when you have kubectl create pod, you have kubectl create deployment. someone did not have to go there and say, here's a create pod command, here's a create deployment command. No, those commands are generated automatically. You just declare the data models. So here's a pod, here's a deployment. The commands are generated automatically. And then controller runtime, I don't remember what it does. Doesn't matter. Now, case studies. So before case studies, I think we're missing a slide here that connects what this whole thing is with the thing that we're trying. And I might as well just add the slide here. What is the thing that we are trying to do with that control loop? So we should probably explain that. So I'm going to explain that. So the thing that we're trying to do is we have an application, Tilt. I'm going to talk about it in a second. It can do a bunch of things. Most programs that you use, most tools, you can click the button or type the CLI command and it does something. You don't know what's going on. You don't know the steps that are happening inside the application. You just have the input and the output. With this API, with this control loop, what happens is you have the same API that you can use to look at many different parts of the application inside the application. So an example would be, let's say you do like run Kubernetes. Let's say there's a run Kubernetes command. It's going to get everything up and running. And then in the end, you have an endpoint that you can see your website. Kubernetes is not just that. With Kubernetes, you can inspect all the multiple steps. You can see, is this pod running? Why is it not running? Why is it failing? Can I change this deployment? Can I edit something? You have visibility over the internals of the application. And then what we're trying to do here is, can we use this exact same API to give this exact same visibility to an application that is not Kubernetes, that is something else? And is that going to be a good thing? So case studies. We're going to use Tilt as an example. So Tilt is the tool, the name of both the tool and the company, which is confusing, but okay. So Tilt is a tool that watches your source code. It keeps your development environment up to date and it automates development tasks. What this means is you tell Tilt, here's all my services. And then, for example, you make a change to your code and Tilt rebuilds your new container. It puts it in the cluster, it updates your YAML, etc. As a developer, all you do is change code and let's say go to the browser to see the changes or go to your Postman or something like that to see the changes. You don't have to worry anymore about updating things and building and deploying and etc. So it automates all those in-between steps for you. Now, the main thing that Tilt does, like the center of everything, is watching your source code. So when you change your source code, something needs to happen. Now, there's many tools that do file watching. File watching is a good thing to use a reconciler pattern for. I used NodeMon before as an example. So it's a very clear case of a control loop. So we're going to watch an environment. When something changes, we take an action. So the events happen at runtime. It's a declarative data model. For example, watch all files that are .go. So you just declare that at the beginning and then the application keeps an eye on it. There's a billion different implementations. So the functionality is the same. The interface to do this is the same, but the actual implementation needs to change depending on the environment. So here's how we structured this. We have an API running. Tilt has been rewritten to use this Kubernetes style API. So we have a spec and a status. And if you're familiar with Kubernetes, you know that everything in Kubernetes is a spec and a status, like you have a pod spec and a pod status. Same for deployments and all the other resources. So here we have a spec for a file watch. It says, here's the paths that we want to watch. Here's the things we want to ignore. And then the status is the part that says there was a file watching event. So a file changed somewhere. There was an error. Your operating system said that you don't have permission to access this or whatever it is. So basically, anyone can see all the file watches that we have running. They can inspect the paths. So maybe I defined, I said that I want to watch a certain directory. There was an error in the syntax. How do I know that there was an error? Usually you would get one big error that's like, oh, things went wrong. Now you can actually inspect the details. Oh, is my watch paths exactly what I wanted it to be? Is the error what I expected to be? I made a change to a file. Did it detect that change? You can just come here and see and like actually inspect the objects inside the application. So before, people would misconfigure things because of the syntax or OS errors. They would never really know what happened. While now, people can run experiments. They can try things out. They can change the spec. They can touch a file and see if there was a change inside the system. Kubernetes auto-generates all the APIs. So you can do tilt get firewatches, tilt explain firewatch name, tilt describe, etc. And you have this reconcile pattern that makes it run. So here's an example of a conversation. Someone was having trouble debugging a firewatch issue because maybe it wasn't catching a file change or something. We just told this person, you can just use tilt describe firewatch and see what's going on. And the person was able to debug everything without any extra help. And usually we would have to handhold users throughout a bunch of experiments to see what's going on. So this is helpful. Another example of a case study for this is kubectl port forward. So when you're trying to connect, let's say you have an HTTP server running inside Kubernetes, and you're trying to access, it's serving a website, you're trying to see that website. So localhost needs to connect to a cluster, it needs to connect to a node. The node is going to connect to the pod's going to connect to the container is going to connect to the server running inside. There's like Kubernetes networking is a huge, it's horrible. I mean, I admire the people who did it, but like it's kind of a nightmare. And the port forward is the thing that connects the first stage to the last stage. So you say Kubernetes port forward, my front end, and it's going to give you an address that you can use to access that. The problem with the kubectl port forwards is they break all the time for a billion reasons. So, oh, you updated your pod, now it's not gonna work anymore. Where's the bug? We don't know. Like, if you actually ask the people who wrote kubectl port forward to help debug issues, and here's an example of a thread like that, they're gonna tell you just kill the port forward and start a new one. It's too complicated to debug. We don't care. It doesn't matter. So we were thinking, well, if that's how it works, can't we just make it kill the port forward and start a new one automatically? And then basically we did that. So we forked kubectl port forward. We made it into a controller. It has that same structure that you've seen before in the firewatch. We're using this reconcile pattern. And basically now, because you can see all the internals of it, the same way as I showed with the firewatch, it's much easier to debug. It's much easier to get a controller to like, okay, just kill this and start again already because it's not worth debugging it. So like we just kill it, restart it. The user never sees anything going on, but where things would previously break, now they just magically work. And when we do need to debug it, it's easier because you have more visibility over what's going on. So yeah, before it was one big mega bug of people yelling it doesn't work. And now people can diagnose with more specific information. They can use the CLI to make more specific changes. Like if you, for example, if you have a controller in charge of port forwards, your port forward is wedged, you can just delete it. And the controller is in charge of creating a new one in place of it. So it's self-healing. So basically everything is better. Things self-heal. You have more visibility over the distinct issues that consist of bug. And it's easier for us to help users. So lessons. How is this making things better? We have changed basically all the functionality of tilt to follow this model. And that means that every bit of functionality inside the application follows this object controller model. You can inspect any bit of functionality from tilt using the same verbs, using the same API. It's the same way to debug it, to inspect it, whatever. Everything is uniform. You can interact and watch any element of the system in the same way. So are you a user on the CLI? Are you in binary code that we who work at the company put inside the tilt binary? Are you a separate binary, maybe a dashboard that someone wanted to give different visibility over different aspects of the system? Wherever of those it is, you're going to interact with the API in exactly the same way. It's uniform for everyone. And that makes something really cool, which is now it's very easy for us to prototype new features. And it's very easy for users to add features that they want that we didn't implement. So for example, You can see here, there's a bunch of resources here. And when I change the source code, it rebuilds, etc. So let's say you have a resource that takes a long time to rebuild. Maybe it's Java. So when you change your code, it needs to do a bunch of steps to rebuild, and it takes some time. But let's say you made a change, you saved your file, and instantly you realized, oh, I forgot a detail. So you don't want it to rebuild. You just want to stop rebuilding. You're going to fix the detail, and then it rebuilds again. We wanted a button that it's like that it goes here in the corner that could just cancel any build halfway through. And like, can we add that feature very cheaply? And the story is we can come here, tilt, get commands, and watch. So basically this is, I'm telling the API watch for a certain type of object. Magic, when that watch change sends me any events, I'm gonna run this this button shell script with the name of the thing that happened. So the thing, the bash script is then gonna say, okay, I want to create a new button, and here you can see we have a resource called UI buttons. And like I said, everything in the application now uses the same API. So to add buttons to the UI, it's just a new object that you create. So I'm going to add a UI button. It's going to be called cancel, and whatever the name of the resource is, it's going to be attached to the resource. It's going to say cancel. And I think we don't have the actual command that runs, but it's basically a kill, like a get the kill PID. I think it is. I might be wrong. I don't remember. But anyway, it runs a thing. So I say here, watch the API for events of a certain type. When you get those events, create a new API resource, and then voila, you can add a bunch of buttons here to the corner, and this is just a screenshot of other buttons. But for that one, it would say cancel, and then you would have a bunch of custom buttons here attached to every resource, and then you can cancel those builds. So everything in Tilt now uses that. So we have a standard interface, file watches, Kubernetes discovery and deploy, which I could give a whole talk about Kubernetes discovery, and a colleague of mine actually has. Image building uses, like, building an image, also an API, like you need to build a new Docker image, create an API object using the same thing. Tilt's gonna take care of the image being created for you. Live reloading to make changes at runtime, etc. Everything uses exactly the same API. Using one single API puts pressure to keep things simple and modular and avoid complexity. Lots of times people want to say like, oh, I'm only going to do this once, so I'm going to cheat. I'm not going to make it the way it should. It's just a one-off thing here. And then, over time that builds into a huge snowball. With this system, you can't do that because like the API is very, you can only add things to the API in a certain way, and that certain way is necessarily flexible, modular, etc. You don't have to re-architect or do any big planning when you add new features, because you are basically stuck to that API format. And that's a good and a bad thing, but there's something a colleague of mine said, which is when you pick someone else's library, you get a bunch of opinions for free. In the case of Kubernetes, those are generally good opinions. And I'm going to talk about the bad ones in a second, but generally you're forcing yourself to adopt a bunch of good opinions. It is a system that is mature, that is stable, that scales. So you're basically forcing yourself to follow this system that it works. Yeah, so let's talk about you. How do you know if your application should use an API like this? It's a matter of 1, visibility, and 2, unpredictability. So is your system something that users are going to want to inspect the insides of? If you're working on a development tool, probably the answer is yes, because developers have very different environments, very different ways of doing things. Developers don't just want, oh, take an input, do magic, here's the output. We generally want, take some input, tell me exactly what you're going to do with that, and then give me the output. So if you need that visibility, then this kind of an API is helpful. If you don't, then not really. For example, an exception to what I just said is compilers. Of course, every one of us here has already went to look at the source code of a compiler to see how it was doing things, and it's fun and it's cool. But generally, you just want the binary. You give it source code, you want the binary, you don't care what the compiler is doing. Same thing applies, like, oh, is your application Facebook? You know, when my mom posts a cat meme, she does not care how Facebook works at all. She just wants, here's the input, here's the output. So if your system does not, if users of your system do not care about visibility on the insides of it, you probably don't need a system like this. And the other element is unpredictability. So with Kubernetes, who knows what's the new resource type that's going to come up tomorrow? We don't. It is made to, it has unpredictability built in. It has CRDs, which is basically, I don't know what you're doing, but you can add a new thing here and it's going to work on that same control loop. So the arrow spike operator, it's probably a CRD. It's basically telling Kubernetes, here's a bunch of my own stuff that I'm doing, run it through the same control loop. But the people who wrote Kubernetes don't need to know about arrow spike. Arrow spike can just go in and add its stuff to the system. So if that element of unpredictability or customizability is important for your application, you probably want this. Okay, getting to the last final bits here. We got a lot of features for free from kubectl because the kubectl people are smart, and because we're basically forking their stuff, this is good. For example, like I said, it's a robust system. It's not gonna die on you once things scale up. There's a lot of stuff you get there, like, let's say some people like YAML, some people like JSON, etc. You get all that flexibility because kubectl has that flexibility. Something that's important, and if any one of you is working on developer tools, this is important. Social conventions are a very helpful thing. If you start using Tilt today and you need to inspect a Firewatch, if you already have experience with Kubernetes, you can just go and do it. You already know how to do it, even though you maybe hadn't heard of Tilt before this talk. You can go and inspect any element of it because you speak Kubernetes already. So that familiarity, that speaking the same language is huge. It's a great thing. Things that are bad, that we are not so happy with about having used the system. So Go versioning is annoying. In Kubernetes, it is more annoying. And it doesn't sound like that big of a deal when I say it, but if you look at Jason the Tibra's talk, in which he was basically implementing the same thing, a very similar way of using the Kubernetes API for unrelated applications. He was implementing the same thing and he had a lot of trouble with Go versioning. So you should check out his talk if you're interested in that. A lot of people have, shit talked gRPC rolled around. I don't need to add to that, but it's there and it's a thing. So it's something to pay attention to. We are, though, very happy that people at Kubernetes, which is the main Kubernetes repo, have been breaking it into smaller parts, so that helps. Another thing is, like I said, you inherit a lot of opinions when you adopt someone else's architecture. Some of them, most of them are good. Some of them were not so good. So API server from Kubernetes defaults to etcd storage. We have no interest in using etcd at Tilt. And you might think that re-implementing a storage interface is easy. It sounds easy on paper. It's not easy in practice. So if you're going to have to do these things, they're going to have a cost. And it might be not trivial. Another point on inheriting people's opinions is the Kubernetes API security model is quite robust. It does everything over TLS. There's a lot goes into that. For a local tool that's running always just on localhost, not talking to the outside world, we don't need that. So for Tilt, we didn't need that, but we didn't remove it because it would be too much work. It's best that we just use the same code Kubernetes is using, but it's overkill. So that's something to pay attention to, like the architectural decisions that you have inherited. If you want to study this further, there's this project called KCP, which is about doing what we did. So like abstracting, taking the Kubernetes API and taking the Kubernetes out of it so that we're left with just the API and then using that API for other things, sorry. That idea is the one from Jason that I mentioned before. It's also a similar idea. In the future, it would be cool if people could use this API, this Kubernetes style API, without having to do a lot of the heavy lifting. we were able to copy a lot of code straight from Kubernetes and it just worked, but a lot of it we had to adapt, and that's a lot of work. If there were a system that's like a Django Rails for this type of API, that would be great. I do think lots of applications would benefit from using this scaffolding. I think it is the next thing. Like everyone uses basically Cobra to do their CLI things, and I think this could be the next Cobra, but for API structure. So that would be great, but right now we don't have that. But people are working on it, and hopefully we're going to have it soon. That's what I had to show you. And if you have questions, they are welcome.
Thank you.
One thing. Thank you. Yeah, thank you very much. That's a nice talk. Do we have questions too?
You can also write your questions in the chat if you don't want to talk.
Did that make sense?
Also feedback.
Yeah.
Yes.
Everybody's busy digesting the talk, kind of.
Okay, Marcus said it did make sense, so I'm happy about that.
Thank you, Marcus.
Yeah.
Good feedback.
Yeah.
Yeah.
Or at least not without an explanation, right?
Yeah.
The slides are worth nothing without the voice to
I mean,
it.
I told him to just add things and that I would review it before the talk, so it's my fault for not reviewing.
See, it worked.
Yeah.
But at least we had fun.
I must admit, I'm slightly horrified by the whole. So stuff just breaks in Kubernetes, and you don't know why, and it's just magic, and you're only, just turn it off and on again, and it will magically work next time as an approach. It just that horrifies me. That's like, yeah. I mean, I get the whole approach that individual servers are just cattle, not pets, but